The original Bohr model was for an electron going around the nucleus of the hydrogen, which has one positive E charge. There are a couple of interesting variations, easy variation of the Bohr model, which allows us to look at things that can be solved with the Bohr model, but with a slight twist. First of all, it doesn't the nucleus doesn't have to have only one positive charge. You can have a number of positive charges. For example, you can take a helium atom, right? A helium atom has two positive charges in the middle, two protons. Okay? And normally has two electrons outside. But if I take one electron out, so it becomes a helium ion, okay, ionized, then this is really just one electron orbiting around a nucleus which has double the charge of the proton, 2e. This can also be described as the Bohr model. So the helium ion is equivalent to the Bohr model applied to the case where this E for the positive charge becomes 2e, so we just have to take this positive charge and make it Ze. How does that change the energy and everything? Well, let's go back to the energy expression. Okay, let's see here. Let's see here. This is the force between the positive and negative charge. The only difference is that now there's a Z here. Okay, Z equal to 2 for helium, equal to 3 for lithium, and so on. All we have to do is change the E squared, which is E times Z, to what? E times ZE, right? So every time you see an E squared, put a Z in front of it. That's all you have to do. So the answer here, e to the power 4. Now e to the power 4 is E squared times E squared. Every E squared now becomes ZE squared, so there's an extra Z squared here. Otherwise, it's just the same. Okay, so you see the Bohr model can also be used to describe the behavior of any atom if I take all the electrons out, leaving but one in there, such as helium ion, such as lithium plus plus. You take 2 out of the 3 electrons out, you get the same as the Bohr model. Another thing we notice is that there is actually a small correction to the mass of the electron we should be using. We have assumed that the electron simply revolves around the nucleus, and the nucleus doesn't move at all. This is an excellent approximation given the fact that the nucleus is much more massive than the electron. But the nucleus is not itself immobile. It actually moves, okay? But it doesn't move by much compared with the electron because of its mass. In reality, when you deal with the motion of both the nucleus and the electron, this is what's called a two-body system. Okay? Now, in a two-body system, we learned from classical mechanics, from physics 1A, that we can separate the motion into two types. One is a center of mass motion, and the other is a relative motion between these two objects, r being the distance between the proton and the electron. The center of mass part of the motion is trivial because it is governed only by external force. Suppose we're not interested in that, so the center of mass simply is fixed or moves a constant speed. The relative motion part is what we're interested. R is still the same R, separating the two particles, but in 1A we learned that when you go from two body back to one body, look at relative motion, you have to make one change, and that is the mass of this equivalent one particle moving around the center of another body, which in fact the distance is r. R is just separating between these two particles. We still call it r. You have to use what's called reduced mass. It's called reduced mass because it's less than the mass of the electron. The reduced mass of a two-body system, which is suitable in describing the relative motion between these two bodies, is mass of the first particle times mass of the second particle divided by the sum of these two masses. And this is less than the mass of the smaller one, right? Because it's mass of the smaller one times this ratio. Look at this ratio here. This ratio is less than 1. It's less than 1. But if the mass of a proton is far greater than the mass of the electron, which is true, by the way, the mass of proton is about 1840 times the mass of the electron. Okay, it has almost all the mass of the atom. And then this ratio, even though it's less than 1, it's almost equal to 1. Almost equal to 1. So it's like 1840 divided by 1841. So the correction is pretty small for the case of the hydrogen atom. You have a tiny correction by changing m mass of the electron to mu. But this can change if I look at a different setup. For example, if I replace the electron with another particle called a muon, a negatively charged muon, this guy has all the same characteristics as the electron, except it's got a lot more mass. It's got about 206 times the mass of the electron. So instead of 1 over 1840, you get 206 over 1840. That is not that small anymore, right? So when you look at a muon atom, sort of, so to speak, muon atom, so you consist of a muon and a proton, you must use mu instead of the mass of the muon, because the correction is not that small anymore. And better yet, we can also imagine a case where a positron and an electron revolve around each other. So what's a positron? It's a positively charged electron. That's what it is. And you have an electron. They attract each other, of course. One positive, one negative. They attract each other. So they can form some sort of pseudo atom, so to speak. It's called a positron-electron pair. And in this case, the reduced mass is substantially different from the mass of each particle. These particles have the same mass, they just have opposite charges. So it's m squared divided by m plus m, and that is only half of the mass. So if you want to describe an electron-positron pair correctly using a Bohr model, you must use half of the mass of each positron or each electron in order to get the correct answer. Another thing we can think about is that Bohr started using only circular orbitals of the electron going around the proton. But the thing is, the electron-proton force is 1 over r squared, and that is the same as what? The gravitational force between the Earth and the Sun, right? 1 over r squared. And we know that classically, if you have a force of 1 over r squared, inverse squared nature, the general expression for a particle going around the attractive center should give you an elliptical solution instead of just a circular solution if the total energy is less than 0, which means that it's a bound state. So can we extend the circular orbital to elliptical orbital? So think of this positron as the sun and the electron as the Earth. The Earth goes around the sun in an elliptical orbital. Can we extend the discussion to that case? The answer is yes, we can do that. You still have the same conservation of angular momentum. And not only is the angular momentum conserved, it is also quantized, just like before. The answer you will get, it remains the same, even though the orbital is now elliptical. You can think about that as well. But does that mean that the hydrogen atom is just a miniaturized version of the solar system, with the sun, with the proton resembling the sun and the electron resembling the Earth? Well, it turns out that is just wishful thinking. Okay, the microscopic world is very different from what we can see, because we have to use a wave function to describe it. Everything is probabilistic, not deterministic. Unlike the case of a solar system, we can predict exactly where the Earth will be. Instead of using only a probability to predict where it might be, how likely it might be. Now let's go back and take a look at the centerpiece of the Bohr model, and that is, in order to introduce the quantization of energy, Bohr hypothesized that the angular momentum of an electron moving around the nucleus must be quantized, that is L equals nh bar. Without that, you're not going to have any good agreement between theory and experiment. And the question we want to ask is, where does that come from? Okay, where does L equals nh bar come from? Can we justify that? Well, it turns out the full justification belongs to quantum mechanics, so we have to use Schrödinger's equation to revisit this problem, which we will do in the next lecture. But within semi-classical approach, that is within Bohr's so-called old quantum mechanics, can we get some reasonable interpretation of this hypothesis? Well, it turns out to some extent, yes, we can. Let's see how we can do that. Now we know that according to the de Broglie relationship, the momentum and the wavelength of a particle is related by this expression P equals mv, which is h over lambda. That's the de Broglie relationship, right? So a particle with momentum p is associated with a wave of wavelength lambda. we can actually solve for that wavelength from h over mv. And for this particular case, we have an angular momentum L of this particle. L has a magnitude of mvr, which is p, which is p times r. And therefore, mv itself is just the angular momentum divided by r, the orbital radius. Remove that r over, I get hr over L. And then here is h. Let me rewrite h in terms of h bar, which gives me h bar times 2 pi. Move that 2 pi over. You get 2 pi r here, right? You get 2 pi r here. Now exchange lambda and L. I get L equals h bar times this thing here. Why is it that L must be h bar times an integer n? I know that L is actually h bar times this guy. So the question is this guy an integer? If so, why does it have to be an integer? Take a good look at this. What is 2 pi r? 2 pi r is the circumference, right, of this orbit. What is lambda? Lambda is the wavelength. You know what that means? If you draw a wavelength pattern of the wave that accompanies this electron of linear momentum p, you're going to get something like this, right? Okay, you could draw a whole bunch of wavelengths. Now, the wavelengths must seamlessly come to, the wave must seamlessly come to the original wave when you go around the circumference once. In other words, the wave must be periodic. Okay, therefore, this circumference must contain an integer number of wavelengths. Circumference must be integer number of wavelengths. Otherwise, you're going to missing a half waves or whatever, and it's not going to combine seamlessly to form an infinite loop like this. This is to say that 2 pi r, the circumference, must equal to a integer multiple of wavelengths, and that's exactly the same as 2 pi r over lambda equals n. 2 pi over lambda equals n. So this is why it is equal to n h bar. So semi-classically, we can argue that the Bohr's quantization condition for the angular momentum really is the fact that the wave, the de Broglie wave for this electron must be periodic over the circumference of the Bohr radius. That's why. But please don't take this too seriously, because this is only a semi-classical approach. It is not the ultimate theory as to why the angular momentum is quantized, which is a direct result of solving Schrödinger's equation, which we'll see in our next lecture. Now let's take a look at what's called the correspondence principle. It was first proposed by Bohr. In fact, Bohr used this correspondence principle in helping him deriving the energy expression for the hydrogen atom. What is the correspondence principle? In physics, correspondence principle tells us that if you rewrite a new theory in order to cover a region where the old theory fails to be valid, then as you go back to the region where the old theory is valid, then the result of the new theory should go back to the result of the old theory. In fact, we saw that in relativity, right? We saw that if V over C is far less than 1, then all the relativistic expression should go back to classical expression. The kinetic energy goes back to 1/2 mv squared, as expected. Gamma reduces to 1, T becomes T prime, and so on and so forth. This is a very natural thing to do, because after all, the new theory just enlarges the boundary of application of the old theory. But when you go back to it should include the old theory when you go back to the within the boundary of validity of old theory. But here in our case, we have a very peculiar situation, because it looks like the frequency of the light emitted by this hydrogen atom, it has very different interpretations in classical and quantum mechanics. In classical physics, when an electron goes around an orbit, it will have revolve at a certain frequency, right? Just how many times it goes around the orbit, the center of the orbital once. This has nothing to do with the electron jumping orbitals. It stays in the same orbital, but how frequent does it turn around? That frequency, according to classical physics, is also the frequency at which the electron will emit radiation. So you see, the electron doesn't really jump orbitals in classical physics. It just keep on turning and turning with this frequency, and that's the frequency you're going to observe. On the other hand, in quantum mechanics, the electron does not radiate anything when it stays in one orbital, no matter how fast, how slow it moves. In order to emit a photon of frequency f, it has to jump orbitals. Okay, let's say jump from the n plus 1 orbital to the nth orbital. The energy difference is E of n plus 1 minus E of n. You divide it by h, you get the frequency of the photon emitted in the quantum description. So the first case, there is no jumping of orbital. The second case, there is a jumping of orbital. These are totally different ideas. How the frequency of the light can be observed, totally different ideas. However, nonetheless, according to the correspondence principle, if you go back to the region where classical physics is valid, these two drastically different frequencies will have to be equal to each other. How do we go back to classical physics? Well, we can look at very large value of the quantum number n. When n is very large, the energy becomes very large, the size of the atom becomes very large, we go back to classical physics. Okay, so let's take a look at what happens when n indeed is very large, say a trillion or a trillion, whatever, a ridiculously large number. Is it true that these two frequencies go back to equal to each other, even though they came from very different concepts? Let's see. Okay, I'm going to rewrite the Bohr, the classical expression for the frequency a little bit using the quantization of angular momentum nvr equals nh bar. Okay, so F classical. The reason why I want to do this is because I want to eliminate one of the two variables, v or r. You want to keep only one of them. Okay, so I eliminate Rn, which is now nh bar over mvn. You flip that vn over this mv squared over nh. Why h? Because it's 2 pi times h bar, that's h. So you have here mvn squared, which is mv1 squared over n squared, because vn equals v1 over n. Remember that? Okay, and let's continue. Okay, mv1 squared is twice as much the total energy in the first Bohr orbital, which is the ground state energy. So this part, mv1 squared, is just E1, absolute value. Okay, and then you have 2. There's a 2 here because there's a 2 there. There's a 2 here, and there's an h, there's n. Now, you have an n squared combined with this n, so it's 1 over n to the power 3. So that's how I rewrote the classical expression. Now, the quantum mechanical expression, which involves an energy jump from one orbital to the neighbors. Let's see how we can do that. F quantum, okay? I rewrote En plus 1 and En in terms of E1. That's, it always goes like even absolute value divided by n squared. So you have this, right? You have this. Let me work this out. This is n squared times n plus 1 squared. In a denominator, a numerator is this thing squared minus this thing squared. What's left is, there's actually 2n plus 1, okay? 2n plus 1. But who cares about plus 1? Because 2n is very, very large, so 2n plus 1 is just 2n. There's an n here from 2n, and there's another n, there's an n squared there, right? So you cancel 1 power of n, then you get 2 over n times n plus 1. But even that can be simplified because that n plus 1 is just n when n is very large. So again, you get n to the power 3 with the rest of the expression being 2e1 absolute value times divided by h. You see, these two expressions magically agreed with each other as n approaches infinity. This is stunning. As a matter of fact, historically, you know how Bohr got the quantization condition for angular momentum? He actually used his correspondence principle. So he was not totally clueless. He used the correspondence principle. He said, okay, these two expressions must agree with each other. In fact, you can derive, believe it or not, you can derive the quantization of angular momentum from, which is this expression, by demanding that these two expressions be equal. So what we did was the other way around. We said this is already true, so then we proved that these two are equal. But if you demand these two are equal, you can go back and derive this. That's what Bohr did. So therefore, the correspondence principle is not only correct, but also it's powerful because it can, in this case at least, it gives us the Bohr's quantization condition for angular momentum. Now, I must say that his derivation was not without any question, because he did have to make one assumption, which is not that obvious. And the assumption is that as you go from one orbital n to the next orbital n plus 1, there is a gap, there is a difference in angular momentum, right? Delta L, right? He assumed this delta L is a constant. Okay? In other words, you go from n equal 2 to 3 or 3 to 4 or 4 to 5 and so on. Every time you jump one orbital to the next neighbor, the angular momentum changes by only the same unit. So there's an even spacing of the value of the angular momentum. This is not obvious. If you look at energy, for example, the energy expression, delta E is never constant except for the case of simple harmonic oscillator. Otherwise, delta E is not a constant. So this is not quite all that convincing because you have to make this assumption. The true meaning of the conservation of angular moment and the quantization of angular moment, I should say, lies with the solution to the Schrödinger's equation for this particular Coulomb potential. This will give us an exact understanding of why the angular momentum is conserved. So all we have done here, despite its great success, we are only dealing with Bohr's semi-classical model or old quantum mechanics. The new quantum mechanics treats the hydrogen atom in a different manner. We don't have to do any of these, hypotheses, concept, the quantization of this and quantization of that, whatever. All we have to do is write down the Schrödinger's equation for the hydrogen atom. It's a three-dimensional equation with Coulomb potential as the potential, and we just go ahead and solve it. We solve the wave function, and from the wave function we can find the energy, and it turns out energy will be quantized, and the photons coming out of the system when energy orbital is jumped will agree with the experiment, and the quantization of angular momentum turns out is just a natural outcome of the solution to the Schrödinger's equation. So that would be what we see in the next chapter.